Dear participants, in this session we will be concentrating on experiment number 3 of section 1 IABOC 105. Here we will go for study of NPN transistor characteristics in common emitter configuration. The manual consists of necessary theoretical background that is required to work with a transistor, definition of different transistor characteristics, operation modes of bipolar junction transistors. They have all been discussed with necessary detail. Now we are particularly interested in common emitter configuration of the transistor because this is very well applied and it can find extensive application. That's why we will be concentrating particularly on common emitter configuration for this experiment. As we all know that transistor is having three terminals, in which in common emitter configuration the emitter terminal is made common. The input signal is fed to base emitter junction and the collector emitter junction is considered to be the output part. Okay, now you see here we will be studying input and output characteristics. All right, in which what we have to do while studying the input characteristic, we have to keep collector to emitter voltage, that is VCE, constant, while we will be changing the base potential, that is VBB, and we will be observing the values of emitter current and base emitter voltage. While performing the study of input characteristic, we should be very clear that collector to emitter voltage should be kept constant. Now you can see this is the characteristic curve, typical characteristic curve, in which you can find two characteristics. There is nothing to be worried. We have to remember that whenever we are performing such experiment, we perform it for different values of VCE. Different values of VCE. Okay, so that's why it is written that input resistance is nothing but change in VBE divided by change in IB, while VCE is constant. Now again, if we go for studying the output characteristic, then we have to remember that base current has to be maintained at a constant value. Alright, and after that we have to change the collector to emitter voltage, that we can accomplish by changing the VCC. VCC means the voltage that is being applied to the collector, that we have to change, and we will observe what is the change in collector current. So the characteristic is something like this. Again, you can find there are three sets of values because we are using IB1 for first case, IB2 for second case, and IB3 for third case. That is base current 1, base current 2 and base current 3. We can observe very clearly that if we increase the base current, then there is increase in collector current. This is a very I should say common observation that everybody can follow. And now you can find here uh, just to make you aware that transistors can be available in different packages, right from plastic package to ceramic package, metal package. Every sort of package is there to accommodate them in a very wide strata of applications. We will be using here this particular package, okay, and in this particular package, that is TO18, these three terminals you can find emitter, base and collector, they are there. And with this TO18 package you can find one notch. You can find one notch. The terminal that is nearest to the notch is emitter terminal. And after that, if we move simply clockwise, then we will find the first one is emitter, then there is base, and finally there is collector. Likewise, there are different means by which you can identify terminals for different packages. So while you want to connect them to the circuit, be very careful about proper identification and connection of the terminals. Otherwise, your circuit will not work, and moreover your transistor will get damaged. Now you see here the components that will be required are transistor CL100 that we will be using for this experiment. The resistance values required are 220 kilo ohm and 560 ohm. In our case, we have used 100 kilo ohm and 1 kilo ohm. Now you see the maximum collector current that is allowable through the transistor is 1 ampere. Maximum collector to emitter, you can see here, VCO max is 50 volt and EBO max, emitted to base, that is 60 volt. So whenever we are designing a circuit, we must remember these extreme values. Otherwise, it may so happen that we are making the circuit for large voltage operation and that voltage might damage the diode transistor because of our ignorance. Therefore, you should be very careful with these extreme specifications at least, and it is always better to go through the data sheet of the transistor. We have already provided the data sheet at the end of this manual. The list of equipment is simple. We need a regulated power supply 0 to 30 volt. Now here, if we want to, okay, here we actually need two regulated power supply. The quantity has to be changed because we have to concentrate on the collector circuit as well as the base circuit. So we need two power supplies here. One digital ammeter, two digital ammeters are required and two digital voltmeters are required because here we will be continuously or concurrently we will be noting the voltage across base and emitter, that is VBE, the current through the base, that is IB. We will be concentrating on collector to emitter voltage and this collector current. So you can see over here that for input characteristic, what you need to do, you need to keep the collector to emitter voltage constant. That's why you can see here the two power supplies are there. With the help of this power supply, that is the power supply on the collector side, we maintain a constant collector to emitter voltage. And with the help of the base power supply, we are changing the base current. Now you see here, this power supply is designated as VBB, not VBE, because VBE is the potential drop across this or the voltage developed across this base and emitter. Okay, that you have to remember. Supplies are always indicated with such double subscripts. Likewise, the collector power supply is denoted as VCC. Okay, now you can see here we need not to connect an ammeter because we are not interested in recording the or observing the collector current. We will simply add the voltmeter, and after that, while changing the power supply, we will be changing the base current, and because of that, what is the VBE that is developed, that we have to note. We can do this for different values of VCE. So initial value can be 0 volt of VCE, then we can go for 5 volt of VCE, or you can go for higher voltages also. Now, so far the output characteristic is concerned, now you can find that VBE is no more important. What is important is the value of IB. So we have to have different constant values of IB. and with such constant values we need to change VCE from 0 to some finite value so that there is change in collector current. So here we vary the collector voltage. This is the collector voltage power supply. We will vary that, according to which there will be change in collector to emitter potential and there will be change in collector current. We have to read the value of collector to emitter voltage and collector current. Now remember that while performing these experiments you should be careful to be sincere enough so that you take values for different set, you take readings for different set of values. So here you can see for input characteristics your initial reading set of reading is taken with VCE at 0 volt, and next you can again have a different set of reading with VCE at 5 volt. So this is important to have at least 2 to 3 curves of that family. You should not stop with one curve only. You should have a family of curves so that you can be sure about the operation at different domains of this VCE in case of input characteristics and IB in case of output characteristics. Now you see here, in case of output characteristics, we have to keep the VBB constant so that we can have a constant IB. So you have to vary the VBE. Once you receive a particular IB value, that is base current, you have to keep that constant. Then you have to vary the VCC, that means this power supply gradually, so that you can have from 0 volt to maybe 15 volt, okay, of collector voltage. Accordingly you will be getting different collector to emitter voltage and different values of collector current that you need to record. Okay, so these are the observation tables. You can see for input characteristic for different values of VCE you are recording IB and VBE, and in case of output characteristic for different values of base current you are recording VCE, that is the collector to emitter voltage, and collector current. Finally you have to plot the graphs. Here we are concentrated only on positive axis, so on x-axis please note down the VBE, and in y-axis you note down IB in case of input characteristics, and for output characteristics you note down the values of VCE in x-axis, positive x-axis, and values of collector current in positive y-axis. Now remember, you can see here that we have shown here readings for different set of values. Now you can see the first curve is recorded when VCE was at 0 volt, the second curve is recorded when VCE was at 3 volt, and the third curve is recorded when the VCE was at 5 volt. Alright, so you can conclude from here actually that when we raise the value of VCE, then the cut in voltage, the voltage at which the base emitter diode starts conducting, that gets increased. Again, in case of this output characteristics, you could find that when you raise the base current, when you raise the value of base current, you get higher collector current. So these are the basic ideas. You have to calculate input resistance, output resistance, okay, and that's about it. We will perform the practical right now and see that whether what we have studied about transistor in theory as well as the discussion that took place here, whether that are completely in inclination to the behavior of actual transistor. Friends, let us now concentrate on the actual circuit of this NPN transistor in common emitter configuration. Here you can see this is the circuit. This is a very generic type of circuit and made in such a manner that we can make the connections very easily. So we will get into the circuit first. I will zoom in a bit. And you can find here, this is the transistor, and here you can see the notch. So nearest terminal to the notch is the emitter. So this is the emitter terminal. After that there is the base terminal, and then there is the collector terminal. You can find very easily that the collector terminal is connected to the body of the transistor. Okay. Now you can find that on this side of the transistor, that is on this side, we have got the collector circuit, and on this side we have got the emitter circuit. There are two resistances in the circuit. This is collector resistance and this is the base resistance. Now let us look into the other connections. You see, the connections are really very easy. However, in order to accommodate several meters and two power supplies, such large number of wires are there. So we will go into them one by one. First of all, I will again zoom out a bit so that we can see the power supply. Okay. Now you can see this is a dual channel power supply, and this channel is used to supply the base circuit. This channel is used to supply the base circuit, and this channel is used to supply the collector circuit. Okay. Now you can find there are 4 meters in the circuit. The yellow digital meter, this is the yellow multimeter. We will use it for measurement of VCE, and this green multimeter we will use it for measurement of VBE. That is, here we will be reading collector to emitter voltage, and here we will be reading base to emitter voltage. Now you can find these two very odd man out type ammeters. I have used them deliberately so that we can differentiate. It is easy to follow. This is the microampere which measures the base current, and this is the milliammeter which measures the collector current. Now you see here how we have made the connections. Initially I will put this off, and you can see the positive terminal of the power supply. The positive terminal of the power supply is coming to this point. Okay. Alright. Then from this point we have taken the microammeter, the positive terminal of the microammeter. Now the negative terminal of the microammeter is connected to one terminal of the base resistance. You can see here. This is the negative terminal of the, maybe I will be putting the brightness a bit more so that it is easy to follow. Yeah. Now you can find the other terminal of the, or the negative terminal of the ammeter, microammeter, is connected to the base resistance. The one terminal of the base resistance is connected to the microammeter, and the other terminal is directly connected to the base. What does that mean? That means that whenever we are applying the voltage here at the power supply end, whenever you are applying voltage here, that voltage is making the current to go to the base through the microammeter and the base resistance. That means your base circuit is safe. Now let us move on to the collector side. This is the power supply for the collector circuit. This is the positive terminal of the power supply. Now you can see this positive terminal is connected to this point. Alright, you can find it here. It is connected to this point. Now from this point we have taken a connection to the positive terminal of the ammeter, milliammeter, to measure the collector current. Now you see another terminal of the collector current, current meter, that the negative terminal of the current meter has gone to this port. You can see here this point. This wire has gone to this point. Alright, maybe I'll be able to know. It's a bit clumsy. Now here the collector resistance is there, and thereafter after this collector resistance there is the collector terminal. So you can find that this collector is connected to the source through this resistance and this ammeter. So we can read the collector current, and the collector current is limited by this resistance. So it is safe. Now there are two more parameters that we have to record. One is collector to emitter voltage and the other is base to emitter voltage. Now you can see these two terminals, this terminal and this terminal. You can see this terminal is connected to base directly and this terminal is connected to the common terminal. These terminals are fed to this voltmeter, and you can see this terminal, it is directly connected to the collector, and this terminal, it is directly connected to the common supply. This is fed to this voltmeter. So what does that mean? That this voltmeter, we are directly getting the voltage across VCE, that is collector to emitter, and through this voltmeter we are getting the voltage across base and emitter, that is VBE. Now let us start taking the readings. I will not take each and every reading, I will show you only the trend. When you actually perform the practical, then you take the readings cautiously. Now I will put on the power supply. The VCE value, initially we will be going for studying the input characteristics. So the VCE will be at 0 and we will be changing the VBB. And you can see here, I will slowly make the changes. You can see the VCE value is now 0 volt. That is the VCC, that is the collector supply. So the voltage across the collector is 0 volt, collector to emitter. Now I will be slowly changing. Now you can see what we have applied here, 0.4 volt. There is no current in the microammeter. There is, okay, and you can see here there is some voltage developed across the base emitter junction. It is now 0.4 volt, still there is no current. Now you can see near about 0.5 volt you are finding some deflection in the microammeter. Now you can see the current is increased as we are increasing the VBB source. Now you can see there are two important observations that we have to note. One, that initially there is no base current. We slowly increase the VBB. As we increase the VBB, you can see that the VBE is getting increased, but there is no base current. Now once VBE reaches somewhere around 0.5 volt, you can see here that current increases constantly. What does that mean? That means that this is exactly working like a PN junction diode. You can see the base emitter junction is nothing but a PN junction diode. So here the same sort of behavior can be very easily observed. Now you can find the cut-in voltage. I will wait a bit. You can see here the cut-in voltage. Cut-in voltage is the voltage where the particular value of VBE, where the base current starts increasing. You can see here up to 0.4 volt there is no deflection. Now yes, when you are somewhere around 0.45 volt you can find the initial deflection, and after that there is gradual increase. Okay, now we will be applying some potential to the collector circuit. So we will make here the VCE. You can note here the VCE at 5 volt. Yes, it is now okay, 5 volt. Now again we will keep on increasing the VBB and see what actually happens. You have to note this and this reading right now, because VCE right now is constant. So initially you can find VBE is 0 and there is no base current. We will increase. Now you have to be very
cautious here. I am very specific to that 0.4 volt. Now you can find here that earlier when the VCE was 0 and when we had applied 0.46 volt, there was some current that we could read from the microammeter, but now there is no current. Now we will again okay, there is some problem. This all right. Now we will increase. Now you can find. So where does deflection starts actually? Let us go for another attempt. You can see here once it's reached 5.5 volt. Now what is the significance? You can see whenever we are applying some collector potential, this cutting voltage increases. Now we will go for some higher value. Maybe I will go for 12 volt. I will go for 12 volt. Now we will find that cut in voltage will further increase. You can see here. Now you can find even at 0.52 volt of VBE there is no base current, because now it has increased to a significant extent. Now you can find there is the deflection or the gradual increase in current that we can note. Okay, now what we will do, this is the trend of input voltage and current, that is the input characteristic. Now we will go for the output characteristic. Okay, so initially we will keep this 0 and that is VCE is 0, and we will have certain value of base current. I will keep it 10 microampere. So I have kept 10 microampere, and now we will slowly change the collector supply. You can see here, you have to note this voltage right now and this current. I am slowly changing the VCE. Now you can see the initial rise of current here is very fast. Initial rise is very fast. After that it has saturated. There is a constancy that you can read well. Now I will take a gallop step. I will make this base current to be 20 microampere. Now it is 20 microampere, okay, this base current. Again we will be changing VCE. Initial rise is very fast. Then you can see we have reached a constancy in this collector current. However, the main thing that we have to note here, again we will go back to 10 microampere. Okay, and let us now try to see what is the constant value of current. You can see here it is somewhere around 4 milliampere. Alright, now I will change this to 20 microampere base current, and you can see the current is increasing. Now you can find almost 10 milliampere is the constant current. Now I will be increasing the base current, and you can see this constant current value has increased to 15 milliampere. This means that the transistor is working simply as an amplifier, because we know the particular relation beta DC is equal to collector current by base current. Now since beta DC is forward current gain of the transistor, we can very easily confirm here that yes, for a very small value of base current we can get a larger value of collector current. See here that base current lies in microampere and the collector current is in milliampere. So that's all about this circuit. For any of your confusion, put it in the comment box so that we can get to you. Thank you.